Okay, so let's begin. All right. Let's take a look at the first question. A rigid vessel contains a perfect gas of 1 kg, has a molecular weight of 32 and a gamma value of 1.4. The gas is at 5 bar and 300 degrees Celsius. It is then cooled to 1 bar. Calculate the heat rejected from the gas. Okay, so we are asked to calculate this heat rejected from the gas. So keywords here will include rigid vessel. Okay, rigid vessel simply means the volume is fixed. Okay, so what is the equation to apply over here? Okay, let me key in the main equation first. So the main equation that we want to apply here is Q is equals to mCV T2 minus T1. Okay, so this will be the main equations that you want to apply here today. Okay, so we want to find out the heat, or we need the mass, CV, final temperature, and initial temperature. All right, so final temperature, do we have it? Yes, don't have, sorry. We don't have the final temperature. We have the initial temperature. Initial temperature is 300 degrees Celsius. Okay, and so meaning to say that we need to find out the final temperature. So how can we find out the final temperature? All right, we will use our perfect gas ratio, okay, which is P1 V1 over T1 is equals to P2 V2 over T2. Okay, so this is the equation that we're going to use. All right, so P1 we have, P1 is 5. V1 is fixed, okay, because V1 and V2 is the same. So V1 and V2 will cancel off. All right, so we don't need this. T1 is 300 plus 273 equals to P2 is 1 bar, all right, over my T2. Okay, Ken? So from here, we calculate my T2 value. Okay, thank you. So 114.6 Kelvin. Okay, so from here, we can get our T2 value. Okay, so remember, we are working towards using this equation. So we have to find out T2. So this is the reason why. All right. Okay, so we find out the value of T2, which is 114.6. Okay, next. What else we don't have? We don't have CV, right? We don't have CV. Agree? Do we have CV? No. So means to say that we have to work out my CV value. Okay, so to work out the CV value, all right, we will be using equation. Okay, so CV will be equals to R over gamma minus 1. Okay, so this is the equation that we will be using for CV. All right, take note, this equation here is not in your formula list. So if you want to use this, all right, you have to memorize this. All right, okay. So furthermore, we also realize that we do not have R. Okay, but we know that from the formula list, what is R? R naught over M, correct? R is R naught over M. So therefore, we will place in this R naught over M. Okay, so with that, we can put in the values. So what is R naught? R naught is 8314. M is 32. Okay, gamma is 1.4 minus 1. Okay, so let's go. So the answer here will be 649.53 kilojoule per kg Kelvin. Sorry, it's not kilojoule, it's joule. Okay, so this one is in joule because just now the R naught I already used 8314. I didn't use 8.314. 8.314 is in kilojoule. So since I use 8314, so this one the output will be joules per kg Kelvin. So with that, we have everything and we are ready. Okay, so we will use our equation. All right. So mass is 1 kg. CV is 649.52. All right. T2 is 114.6. Okay. Minus away T1, which is 573. Okay, so answer here negative 297739.97 joules. Okay, so that's it. Yes. Okay. So good question. So in this case, if you use 5 times 10 to the power of 5 here, right? Then on the right hand side, you will need to use 1 times 10 to the power of 5. Because if you want to use SI unit, you must use SI unit here also. But the times 10 to the power of 5 will cancel off. Correct. Yeah, so for this equation here, in terms of the pressure, you can have an option. If you use bar, 5 bar, then you can use 1 bar here. The same thing will cancel off one another. Okay. The only thing that is not so flexible is the temperature. So temperature, you must always be in Kelvin. So if the temperature you don't put in Kelvin, all right, your answer will be wrong. Definitely. Okay, any question regarding this example here? Okay. If not, we'll move on. Okay. So the next question. Water flows at a rate of 20 liters per second through a horizontal pipe, whose diameter is constant. The pressure drop across a valve in the pipe is measured to be 2 kilopascal. Determine the irreversible head loss of the valve and the useful pumping power needed to overcome this pressure drop. Okay, and so today, all right, we have a pressure drop across the valve, which is measured to be 2 kilopascal. Okay, and we are asked to find out the head loss of the valve. Okay, so this is the key thing. Okay, so if you need a diagram, of course, feel free to draw a diagram yourself. All right, but it's a simple one. All right, you have a line, then maybe I'll just use this as a valve. Okay, and another line. Okay, then I can mark the first point here as 1, and I mark the second point here as 2. Okay, so we have a valve, point 1 and point 2. So the pressure drop across the valve in the pipe is 2 kilopascal. Okay, so for this question, all right, we have to use Bernoulli equation. Okay, because the only thing that can calculate head loss is the Bernoulli equation. All right, so as I mentioned during class, if and when possible, before applying the Bernoulli equation, right, we must try to find out velocity. So question, can I find out velocity for this question? Can I find the velocity of the flow? Yes, we can find the velocity of the flow by simply using our equation, correct? V dot is equals to AC. Okay, so V dot we have, what is V dot? V dot is 20 liter per second. So change to meter cube, or liter change to meter cube is divided by 1000. Thank you. All right. Then we have our area, which also we can find by using this pi over 4 times your d square. So for your d square, all right, for your d square, the diameter is 3 cm, correct? So again, you must change it to SI unit, which is 3 over 100 square. See. Okay, so come, let's find out the .29 meters per second. Very fast. Let me check the answer. Make sure it's correct. Okay. Can. Three over 100 square. Yeah, I better put a bracket here in case. Okay, so with that, the next step will be to apply my Bernoulli equation. All right. So the Bernoulli equation will look like this, of course, standard. Okay. Okay. So what do we want? The head loss, huh? All right, we want the head loss. So let me just shift the head loss to one side. Okay. So this one will be P2 minus your P1. Sorry, it should be the other way around. P1 minus your P2. Plus your Z1 minus your Z2. Okay, can. So, but you realize that since the velocity is all the same, correct or not? The velocity is all the same. So this one will all cancel off. The height is also all the same. So this one will all cancel off. All right. So the head loss, all right, will only be equals to my P1 over rho G minus P2 over rho G. Okay. And P1 minus P2 given by the question is 2 kilopascal. So 2000. All right. This is water, so times 1000 and 9.1. So this one is simply 0.204 meters of water. Okay. Oh, this question, huh? Yeah, it's all inside the polymer. Okay, Ken, any question? I think this one, this question is quite simple. The rest of the information is not so useful because eventually the velocity head and the static head all cancels off. Okay, Ken? Okay, if not, we'll move on to the next question. Okay, so we have a working fluid steadily at a rate of 1 kg per second through an open system, entering at 10 with a pressure of 5 bar and a specific volume of 0.2, leaving at 30 meter per second with a pressure of 0.9 bar and specific volume of 0.8. The specific internal energy of the fluid leaving is 400 kilojoule per kg, smaller than that of the entering. Okay, so we are asked to determine the power developed by the system. Okay, and so let's take a look at the equation that we want to apply first. So the equation that we apply here will be our non-flow equation, your steady flow equation. Okay, so your W in plus Q in plus M dot H1 plus GZ1 plus C1 square over 2. Okay, then equals to the same thing on the other side. Okay, so this is your steady flow equation. So to use this steady flow equation, all right, we need a few things. Okay, so main thing is we need our H1 and H2. All right, so I highlight here, we need our H1 and our H2 value. Okay, so we know that H is equals to U plus PV. Okay, so this is given to us. H is equals to U plus PV, we know. All right. So today we have the fact that the pressure and the specific volume is this at the inlet. And the pressure and the specific volume is this at the outlet. And the internal energy leaving is 400 smaller than that of the entering. So these three pieces of information. Okay, can. So today, all right, we cannot calculate H1 and H2, but instead we need to calculate what? The difference. All right, the difference between what H1 and H2 because of the information given to us. They say the internal energy leaving is 400 kilojoule per kg smaller than that of the entering. So what we can calculate here is H1 minus H2. How do I know that? Because what is H1? H1 is U1 plus P1 V1. Minus away U2 plus P2 V2. Okay. So in this case, all right, when we have this, we can group the U1 minus U2 together, plus your P1 V1 minus P2 V2. So by grouping them together, we see that you can sub in your U1 and U2. So you see, you group them together, right? So U1 and U2 is what? U1 minus U2 is what? They say that internal energy is 400 kilojoules smaller than that of the entering. So which one is bigger? Entering is bigger, right? So U1 minus U2 is 400. Okay, thank you. 400. Okay, plus the rest you have lah. Oh, P1 is what? 5. Okay. All right. So we can calculate the answer. Okay, so 4 to 8. 1, 2, 3 lah. Joules per kg. Okay, so once we have this, all right, we look at our equation. So based on our equation, they want us to find out the power developed. Power developed is W out. So this is W out is what we want to find. Huh? So the rest of the term don't have, you can cancel off. W in, don't have. Q in, don't have. Potential, don't have. Kinetic also, don't have. Okay. Kinetic have or not? Kinetic have lah. They got speed difference, man. You see, one is 10, one is 30. Have. So only can cancel away the potential. Q out have, huh? Q out is the heat loss. 90 kilojoule heat loss. Okay, good. So all these don't have, cancel off. Okay, so let's go. M dot is 1, 1. Sorry. Maybe we rearrange first. Rearrange first. So W out, all right, is equals to M times your H1 minus H2 plus C1 square minus C2 square. Okay. Minus away, Q out. Okay. Okay. So we retain the W out here. I shift over Q out, so it's minus Q out. I shift over H2, so it's M H1 minus H2. C2 I also shift over, so it's C1 square minus C2 square. So M is 1. H1 minus H2, 4, 2, 8. 1, 2, 3. Plus C1 square is 10, right? 10 square. So it's 10 square over 2 times 9.81. Sorry, over 2 only. Okay, let me just double confirm. Wait. Okay. Minus away. Minus away. Q out is how much? 90. All right. Wait, let me press first. How much? Okay, good. Okay, so that's it. Any questions? Okay. Okay, next one, question 4. Okay, so we have a pressurized tank. All right. There has a 10 centimeter orifice at the bottom where the water discharges to the atmosphere. The water level is 3 meters above the outlet. All right. The tank air pressure above the water level is 300 kilopascal, while the atmosphere pressure is 100 kilopascal. Neglecting frictional effects determine the initial discharge rate from the water tank. Okay, so the initial discharge rate they are referring to is the flow rate. Okay, so they want to know what is the flow rate lah from the tank. Okay. All right. So for this case, what do we do? What do we apply? We simply apply the Bernoulli equation and don't, as in there's only one thing to apply. Understand? No? Yes, you see, the problem with some of the fluid mechanics question is that it seems as though very complicated. But actually, the bottom line is you just have to apply the Bernoulli equation. Even though it seems not related. Huh? Just apply only. Yeah, correct. Anything related to fluid flow will be Bernoulli. Understand or not? That's my point to you. So long as anything related to fluid flow will be Bernoulli. No matter how weird the question seems to be, or how unrelated the question seems to be, it's just Bernoulli only. Okay, if you compare this question to this one, do you use Bernoulli for this? This one is very clear. This one is, okay, I must use steady flow. This one is very clear. Understand? But this one, the moment is not clear. The moment you see only fluid flow, pressure and everything, that means I only apply Bernoulli. Okay. So where do I apply it to? Remember the few rules that I gave you? Yes, we will try to apply it on the surface. It will always be between fixed points. So which 2 points do I want to apply it to? Okay, good. So we will apply it to these 2 points specifically. One is here. The other one is exactly at the outlet. All right. So that is really the first thing that you need to establish. So this one here is 0.1. And this one here is 0.2. Okay. But the point matters. And the numbering don't matter. Yeah, of course. Just don't confuse yourself. Okay. So we'll be using Bernoulli. So let me just go and grab the same equation from here first. Okay. No losses for this case. Okay, why no losses? Because you see the word neglecting frictional effects. Okay. Yeah. Okay, so Z is the height, correct. Let's put in the values. What is P1? Correct. Good. This one is water, right? Water, correct. 1000. Okay. C1, is there any velocity at 1? No, correct. So Z1. Okay, so maybe before I put this, let me write a statement here. Applying Bernoulli between point 1 and 2, taking 2 as datum. Okay, so let me take 2 as datum. So that I don't see negative. So if 2 is datum, what is Z1? 3 lah. Okay. If you take the other way around, your Z1 will be -3 already. Okay, so we try to take a positive value lah. Okay, if can. What is P2? Pressure 2. No. No. 100 kilopascal. Okay, because you see the atmosphere is 100 kilopascal, right? What is 2? 2 is exposed to the atmosphere, correct? So like I say, anything that is exposed to the atmosphere, it must be at atmosphere. I don't care how fast the water is shooting at point 2. It might seem very pressurized. No. The fact is anything that comes out from the pipe exposed to the atmosphere, it is only at atmospheric pressure. So if you have a hose at home, you used to shower, right? You use your thumb to block, you feel like macam higher pressure, right? Actually, it's not correct. What you are feeling is the velocity, not the pressure. Understand? Anything exposed to the atmosphere must be an atmosphere. C2 is my unknown. Okay. Plus minus 0. Right. Okay. So let's go. First term is 30.58 plus 3 equals to 10.19. Right. So I see 2. Correct. But is this what they want? What do they want? Do they just want the flow speed? What do they want? Discharge, right? So they want the flow rate. Okay. So So yes, P dot is equals to A2 okay, so pi diameter is 10 right times my 21.42. Okay, correct. Middle cube. Per questions? Okay. I repeat myself again. Any kind of weird question in the exam or that you see that you don't know what to apply or where to start or how to start, most probably it's Bernoulli already. You just have to force yourself to apply the Bernoulli between 2 points. Make sure you remember my words. No matter how weird the question looks like or how you don't understand the question, there are values there. You just force yourself to apply between two logical points. That's it. Okay, I hope I make my point clear. Okay, next question. We have a nitrogen expands adiabatically from 3 bar 220 to a volume of 0.1. If the initial volume is 0.05, calculate the change in internal energy, the work done, and the heat transferred during the process. Okay. So we have our pressure and volume. Okay, maybe let me just put in a table. Sorry. So what do we have? T1 is 3. T1 is 220 plus 273. Okay, V1 is 0.05. P2, do we have P2? Don't have. T2, do we have T2? Don't have. V2, do we have? 0.1. Okay. And so maybe before I even try to solve the question, let me find out all the unknowns first. Okay. So if we want to find out P2 or even P2, what should I use? Let's take a look at the equations here. So these are my adiabatic equations. All right. Which one should I choose? I can choose the first one. All right. Because I have, what do I have? I have P1, V1, and V2. So I can solve for my P2. All right. So let's go. So, all right. Okay. So let's say I want to apply this. So, but what do I realize? What do I don't have? I don't have the gamma value, right? You look at the whole question. No gamma. Can I solve for my gamma value? Yes. Huh? Okay, I can solve for my gamma value. So how do I solve for my gamma value? We can make use of a few equations, right? So if you look at our equations here, I have CV, I have R. If I have CV and I have R, I can find out my CP. And if I have my CP, then I can apply my gamma is equal to CP over CV. So that is the strategy that I'm going to use. I'm going to find out my CP first. All right. So I have to put on hold first. Okay. So CP minus CV is equals to R. All right. So CP is unknown. What is CV? 0.741. I use 741 now. What is R? Is it HA14? Is R HA14? No, we don't have directly R, but we can calculate R by using R naught over M, which is 28. Okay. So from here, you can get our CP value. One zero. Okay. So with that, what do I do next? Gamma is equals to CP over CV. So 1037.9 divided by 741. 1.4. And the moment I have gamma, all right, I will apply this one. So what is P2? P2 is unknown. P1 is 3 bar. So we just use 3 bar lah. Oh. Okay. V1 is V2 gamma. Okay, good. So P2 is 1.14 bar lah. Oh, because P2, P1 we use 3 bar. So when we get the P2, it will always also be in bar. Okay. Okay, so there's a huge chunk of processing you need to do. So P2 is 1.14 bar. So next, all right, we'll find out P2. Okay, so I will just use my P1, B1, P1 is equals to P2, V2, P2. Okay, so P1 is 3. V1 is 0.05. Over, what is my T1? 47493 equals to P2 1.14 star 0.1 divided by T2. Okay. So what's my T2? Three 74.68. Okay. So we have our P2 and we have our T2. Right. Okay, there's one more thing we need also, which is our mass. We do not have mass. Oh, so to find out mass, we can use our which equation to use to find mass? P V equals to MR P. So P1 3 bar, V1 0.05, M R is 8314 divided by 32. So it's divided by 28. Star your T1, which is 493. So what is your M? 0.102 kilograms. So the moment we have that, we can start to solve the question. So first one, what is my internal energy? So what is the formula? U2 minus U1 is equals to M CV T2 minus T1. So we have everything already, right? So I just sub in 0.102 times CV is how much? 741 star. What is T2? 374.68 minus what is T1? 493. Negative 8942.9 joules. Okay, next one. How do I calculate your work done? Work done, there's a formula, right? What is the adiabatic work done formula? This one, okay. So P1 V1 minus P2 V2 over gamma minus 1. So everything just plug in the formula. So P1 is what? 3 bar, right? So 3, 1, 2, 3, 4, 5 star V1 0.05 minus P2 is 1.14 bar. Star volume 0.1. Gamma 1.4 minus 1. Nine thousand joules. Okay. And the last step is to do what? U2 minus U1 is equals to Q minus W. So what is my Q? Minus 8942.9 plus 9000. Actually, this one you don't have to calculate because this is adiabatic, correct? So what is the characteristic of adiabatic? No. No what? No heat, no temperature, no heat. Understand? Adiabatic, the characteristic is there will be no heat transfer. Q is 0, Because I say already adiabatic Q is 0, The question say adiabatic, right? Ne? Yeah, by right, don't even need to calculate lah. But if, since I calculated already, I just round off to 0. Our rounding off is probably because of our decimal. Because through all our calculation, right, there's some decimal all along the way, right? If I use the exact value, it should be 0. Yeah. So this one, I'll just set it to 0. If you want, I'll just put behind it since a that q equals to. Okay. Yeah. So, but you see, the values are very close. Some sense. Any questions? All okay. Okay lah. Then last question already. Okay. So the last question here, we have a Venturi meter used to measure liquid flow rate of 7,500 liters per minute. The difference in the pressure across the Venturi meter is equivalent to 8 meters of flowing liquid. Okay. The pipe diameter is 19 cm. Calculate the throat diameter of the Venturi meter. Okay. So for this Venturi meter, all right, we have to use the equation. Okay. So either you memorize the equation or you can derive the equation on the spot. So to derive the equation, you have to make use of your Bernoulli. Let me just. Okay. All right. So maybe I'll just derive it. Okay, for the sake of revision. So we assume that this is a horizontal Venturi. So there's no height difference. All right. And we are interested in our velocity. So C1 minus C2 equals to okay. Can. So I'm going to do some manipulation. So I'm going to leave C1 minus C2 square on the left. On the right side, it will be 2G. Okay. So from here, all right, I will need to substitute our continuity equation, which is A1 C1 is equal to A2 C2. Thank you. All right. So based on here, I will sub away my C2. So C2 is equals to, what's my C2? C2 is equals to A1 over A2 times your C1. Okay. So I'm going to replace with this. Okay, so I'll replace this guy. Can? So with that, I will sub out my C1 square. So inside left with better put the bracket properly. Okay. So what's my C1? Okay, so this is the derivation that we have shown in class. And not only that, all right, because what do we need? We need our discharge, right? Which is our V dot. So what is V dot? A1, C1, so which is A1 times square root of this. Okay, and take note, this one is your theoretical flow rate. So what is the actual flow rate? All right, times your CD. Okay, so this is your final equation. So let's sub in the values. So if you look here, the flow rate is 75,000 liters per minute. So I'll straight away sub in from here. So 75,000 liters per minute. So this will be 75,000. Okay. Liters change to meter cube is divided by 1,000. Some more, because this is in liters per minute. So 1 minute is 60 seconds. So also divide by 60. Okay. CD, what is your CD value? What is the discharge coefficient? What is the discharge coefficient? 0.96. A1. The diameter. Wait, let me get the diameter one is 19 cm. Pipe diameter is 19 cm. So what is my P2 minus P1? Is given as 8 meter of the flowing liquid. Okay, so the difference in the pressure drop across the venturimeter is 8 meters of the flowing liquid. All right, so we do not know the density, right? So we'll just put it as density times your G times your 8 meters. All right, because the pressure drop P2 minus P1 is 8 meters of the flowing liquid. So pressure drop is rho GH, right? Oh, so we use rho GH. But you can see that ultimately the density of the liquid, right? What will happen to it? What will happen to the density? You can cancel off, right? Okay, so A1 over there, A2, okay. So your throat diameter is inside here. So what is your D2? I think we better calculate individually. $1.25. Okay. Then whatever that is inside here. Okay. Oh. So this will be 2111.9. Okay, so what do? I bring the 0.0272 across. So 1.25 divided by 0.0272. Then I take the square root, bring over, it become square. Okay. Everybody following? Yes or no? I repeat again. So from here, I bring the 0.0272 across. So it's 1.25 divided by 0.0272. Then the square root I bring across, it become square. Okay. So it become this. Right. So follow the maths. So this is 2G times 8 divided by 2111.9 equals to so I switch the 2111.9 with the bottom side. So this one shift up, this one shift down. So pi over 4, all these can cancel. Okay, the 100 also going to cancel. Okay. Yeah, let me just double confirm something. Yeah. Okay. So 2 times 9.81. Okay. Okay. So this will be 0.926. I switch places. This one I switch over 1 minus 2g times 8 over 2111. So it's 0.926. Okay. So I switch this across and 29 times 8. Sorry, 2g times 8 divided by 2111. I switch across. So it's 1 minus 2g times 8 over 2111. So it's 0.926. Okay, reaching there. Okay. So square root 0.962. So this one d2 square is there got square, don't have square. 37. Where? Which one? This one? This one? I already square root already. Square root of 0.926 is 962. Yeah. I suggest you all take, when you all go home, right, do the calculation yourself. By following me like this, you might not fully understand. 19.37. Correct or not? Doesn't look correct, the answer. Again? Square root of 18.66. Okay, no link. I get 19.37. But it doesn't seem correct. Wait, let me just double check. Yeah, I put 19.37. I got 19.2. But the answer don't look correctly. The throat, how can be 19.37? The throat should be smaller than the pipe, man. So a bit funny. Let me see. The equation should be correct. Just double check. I think the equation should be correct also. Two. Oh. Sorry, because the pressure drop, I know why already lah. This one should be negative. I'll explain why in a while. So calculate again. So this one should be 1.074. Take the square root. 1.037. This one is 348.12. $18.6. Is this you are referring to this 18.6? Which part the answer is not correct as me, not the same as mine? No lah, cannot. Original one cannot be 18.66. No, so okay. Okay, one mistake that I had here, right, is you see P2 minus P1. Right. From the question, what did they say? The difference between the pressure across the venturi is equivalent to 8 meters of the flowing liquid. Before the venturi is P1. After is P2, right? So which one is bigger? P1 is bigger, right? So if I use P1 minus P2, this is P1 minus P2, correct? So this should be a negative sign. Okay, so P1 minus P2 minus P1 should be negative sign. So there should be a negative here. There should be a negative here. So there should be a negative here. Okay. Why? Oh, you use it the other way around. Okay, then correct. Correct. That means your formula is you use the other way around. Can also. Can also. Okay. But never mind, it's good. At least you reaffirm that the answer is correct. So it's 18.6 now. Okay, wait.